Okay, so I've started recording the class already. So let's go. So let's look at chemical equilibrium in today's class. Okay, pay attention. What is the meaning of the word chemical equilibrium? What's the meaning of the word? Firstly, let's look at the meaning of the word equilibrium. If you hear the word equilibrium, what does it mean? Now, pay attention. Now, see, when we say a chemical system, when we say what? A chemical system is said to be in equilibrium. It's said to be what? In equilibrium when there is no observable changes. When there is no what? Observable changes. When there is no what? Observable changes.
Bring it.
Yes, sir. Please help us meet your mic, sir. When there is no observable changes in the property of the system. When there is no observable changes in the what? In the property of this system. You see, if you are asked to define chemical equilibrium, you will say a chemical system is said to be in equilibrium. When a chemical system is in equilibrium, what happens? It means that there is no observable change. There is no what? Observable change in the property of the system. You see, just like I have a knife edge like this, and I try to balance a meter rule on this knife edge in a way that it will not tip. If you are able to balance this meter rule on this knife edge in a way that it did not bend left or bend right, if it is balanced, then we can say, wow, this system is in equilibrium. Why? It's not either shaking left or right. It is balanced, then we can say it's in equilibrium. So in chemistry, when we say a system is in equilibrium, it means that we can't observe anything in the property of the system. There's no what? Observable changes in the property of the system. Then the system is in what? Equilibrium. Now pay attention. In chemistry, what do we call the word system? Pay attention. What do we call the word system? You see, pay attention. System is what we are studying. It is a portion of matter under study. Let me say I have a chemical reaction going on in this beaker now, for example. Let me say I have a chemical reaction going on in this beaker. Let me say in this beaker, A and B are reacting in this beaker now. You see, this beaker that you see here, we call it a system. We call it a what? We call it a system. If you hear the word system, system is what we are studying. Exactly. That is the portion of matter under study. That's what we call what? System. So that's by the way. Now pay attention. You see this word equilibrium is divided into two. The word equilibrium is divided into two. We have what we call static equilibrium and we have what we call dynamic equilibrium. We have what we call what? Static equilibrium, and we have what we call what? Dynamic equilibrium. Hello, pay attention. There is a word we normally use for in physics. Whenever a body is at rest, in physics, there's a way we normally use this. So when the body is at, when the body is not moving, we say the body is at rest. I believe we have heard of this thing before, probably when we are doing equation of motion and projectile. If they tell us that a body is at rest, it means that what? It is not moving at all. So pay attention. Static equilibrium. You can say a body is in static equilibrium when the body is at rest. That is when the body is not moving at all. We say the body is at static equilibrium. Now, what do we now call dynamic equilibrium? Is opposite of static equilibrium. Are you there? Dynamic equilibrium I'm coming. Let me admit someone. Someone wants to join the class. Okay, so let's continue the class. Now, if I say dynamic equilibrium, that is Is the equilibrium attained? Is the equilibrium attained by a moving system? Now pay attention, you get the difference now. If I say equilibrium is divided into two, we have what we call static equilibrium, we have what we call what? Dynamic equilibrium. Static equilibrium is achieved by a body at rest, but dynamic equilibrium is achieved by a body that is what? That is moving. By a moving what? By a moving system. Good. Now you now understand the concept of equilibrium. Good. Now let's now move forward. Let's move forward to the next concept. Let's move forward to the next concept. Let's move forward to the next concept, which is the concept of reversible reaction. The concept of what? Reversible reaction. The concept of reversible reaction. What is the meaning of the word reversible reaction? It's very easy. Now, pay attention. Look at what is here. If I say A plus B, I now use this type of arrow to give me C plus D. Pay attention. You see, whenever you observe this arrow, then this reaction is a reversible reaction. This arrow is telling you that A and B can proceed forward to form C and D. Also, C plus D can proceed backward to form A and B. So what do we now call a reversible reaction? A reaction that can proceed in both directions. Let me help you write it down. A reversible reaction was a reaction that can proceed in both directions. That is, it can proceed from left to right, and also from what? From right to left. It can proceed from what? Left to right, and also from where? Right to left. Exactly. You see, let me tell you the difference between this and D. Look at something like if I say A plus B going to C plus D. Look at this second reaction here. You see that here, I only have one arrow. It means that A and B can only go and form C and D, but C and D can never go backward. So this reaction like this now can only have one direction. This one now only have one direction, but this one has what? Two directions. That is, it can go front, it can also go back. A and B can go forward to form C and D. Similarly, C and D can move backward to form A and B. So that's what we call what? A reversible reaction. Now, pay attention to something. Pay attention to something. Pay attention to something. Tommy, let me jot down something. Okay. Please take notes. Come. Okay. So I want to write down a definition I want us to look at. Now observe. Okay. Okay. So look at what it said. Pay attention, I told us that we have two types of equilibrium, static and dynamic equilibrium. Now pay attention. Remember, see, in chemical equilibrium, we are dealing majorly with reversible reactions. Are we together? We are dealing with reversible reaction. Now pay attention. Look at these two types of equilibrium. One is static, one is dynamic. You see this static, it does not occur here. Because check this reversible reaction. A and B is going to form C and D. Also, C and D is going to form A and B. So this reaction is something that is moving. It is not something at rest. So pay attention. In this topic that we are doing, we are not doing anything in static equilibrium, but we are actually doing something in what? Dynamic equilibrium. Because a reversible reaction, a reaction that is moving, reactants are forming products, also products are forming reactants. So reversible reaction is actually what we are dealing with, and they are always in dynamic equilibrium. So how do we know they are in dynamic equilibrium? The rate of forward reaction is equal to the rate of what? Backward reaction. Are we together? If I say something is in dynamic equilibrium, what do we say? It is in dynamic equilibrium. The rate of forward reaction is equal to the rate of backward reaction. That is, you see this reversible reaction. If this reversible reaction is in dynamic equilibrium, you will say the rate at which A and B are going to form C and D is equal to the rate at which C and D are going back to form A. Are we together? Yeah, good. So that is it. So if this reversible reaction is dynamic equilibrium, rate of forward, rate of backward are the same. Rate of forward and rate of backward are the same. They are equal to each other. They are the same. They are the same. They are the same. Good. So that's that. That's that. That's that. So that's actually a comprehensive introduction to this. Firstly, we discuss that a chemical system is in equilibrium when there is no observable change in the property of the system. And I told us that system in chemistry, or in chemistry or in science majorly, is what we are studying. Are we together? Good. If I'm studying your book now, I will say that book I'm studying is a system. So the part of the universe that is under study is a system. Nice. Equilibrium is divided into two: static equilibrium and dynamic equilibrium. Static equilibrium is the equilibrium that is not moving. The meaning of static means something. Why dynamic equilibrium is the equilibrium that is what? That is dynamic equilibrium is the equilibrium what that is attained by a moving system. So dynamic equilibrium is actually moving. This one, static equilibrium, is not what? It's not moving. Okay, we now look at a reversible reaction. A reversible reaction now can occur in two directions. It can occur in forward direction. Also, it can occur in backward direction. How do we know reversible reaction? You can know them with this arrow. Wherever you see this arrow, this arrow is telling you that what? You are having a what? A reversible reaction. A reversible what? A reversible reaction. This arrow is telling us that what? You are having what? A reversible what? A reversible reaction. This arrow is telling us that what? We are having a what? A reversible reaction. It means that the reaction can proceed forward or backward. So when do we say this reversible reaction is in dynamic equilibrium? Pay attention that throughout this topic, I won't be talking about anything static, because this chemical reaction, it keeps occurring, it keeps moving, it's not at rest. So if I'm referring to equilibrium, have it in mind, I'm referring to this equilibrium, dynamic equilibrium. Please don't forget, we are not doing anything like static equilibrium here. That one, you do it in physics. But dynamic equilibrium is what we are doing. We are looking at a system that is moving. The way A and B are forming C and D, the way C and D are going back to form A and B is what we are looking at. So how do we know reversible reaction is in dynamic equilibrium? Is in dynamic equilibrium when the rate of forward reaction is equal to the rate of backward reaction. When the rate of what? Forward reaction is equal to the rate of what? Backward reaction. When the rate of forward reaction is equal to the rate of backward reaction, that's when we say what? A chemical system is in what? Is in dynamic equilibrium. Exactly. Rate of forward reaction equal rate of backward reaction. Okay. I want to give us another point also. That, pay attention. You see this reversible reaction here. It is only possible in a closed system. I will tell you why. it is only possible in a closed system. Let me tell you something. Let me say I have A plus B going to C plus D. Let me assume that this system is not closed. You will see what will happen now. If this system is not closed, and let me assume that D is like a gas, it's going to escape. It's going to run because you did not actually close the system. Are we together? Okay, let me tell you. Whenever you are cooking your food and you open the cover of the pot down, then you are cooking in an open system. Yes. But if you are cooking and you close the cover of the pot, therefore, you are cooking in a closed system. Are we together? Good. So, assuming this thing is open system now, one of these things can just run away. This D can just run away because it not actually close it. But if you close it, none of the reactor can run away. None of the product can run away because they are actually in a confined system. Good. So for this to be achieved, they have to be in what? They have to be in a closed system. So that's that. That's that. So let's move to the next concept. Now, the next concept that I want to look at is equilibrium constant. Is equilibrium constant. Equilibrium constant. Equilibrium constant. Equilibrium constant. Equilibrium constant can be denoted as Kc. Can be denoted as Kc. Equilibrium constant can be denoted as Kc. Equilibrium constant can be denoted as Kc. Now, pay attention. What they will test you on under equilibrium constant is how to write the expression for the equilibrium constant. Now, pay attention. Let me say I have this equation. Now, pay attention. Our reactants are capital letter A and capital letter B, and our product are capital C, capital D. You see this number that you are seeing beside it? They are the number of moles. They are the stoichiometric mole in the reaction. Good. Hello, guys. If they give you this type of equation, they now ask you to write the expression for the equilibrium constant. How do you write it? How do you write the expression for the equilibrium constant? How do you write the expression for the equilibrium constant? I'm coming. I don't know why people keep joining. It's like we're putting deadline. If you don't join within that deadline, I may not allow some people to enter again. Okay. Let's move. Pay attention. This is how we write equilibrium constant. We say equilibrium constant Kc is equal to the concentration of the product all over the concentration of the reactants raised to the power of the number of moles. Raised to the power of the number of moles. Guys, this is how we write it. Now, pay attention. Let me now use this equation to write the equilibrium constant. Guys, don't forget, to write equilibrium constant, what do we say? Product over reactant. Then you now put their mole, the one that is underlined in red. You put it in power. Now, let's go. Now, let's go. Let's go. Are we together? Hello, let's go. Let's go. Now, look at the product.
Ariola, mute yourself. Ariola, mute yourself.
Okay. Now, look at the product. Yay! Our products are C and D. So, write your products. Now, pay attention. See what I'm going to do. I'm writing my product to the power of the number of mole. C is my product. The number of mole beside it is small letter c. Also, D is my product. The number of mole beside D is small letter d. You can see this is the product raised to power of the number of mole. Then all over, look at look at the reactants A and B. Then put their mole as their power. Put their mole as their power. Then look at B, look at their mole, and this is the expression for the equilibrium constant. That is it. Let me write one for us with an equation. Pay attention. Let me say you are given this equation. and you have to write equilibrium constant for us. Now, let me write it as a question. Write the equilibrium constant. Write the expression for the equilibrium constant. Now, look at it. Our first equation is this. H2 gas, O2 gas, 2H2O gas. So look at it. The second one is 2SO2 gas plus O2 gas, giving me 2SO3 gas. And C, we have Fe solid plus 4H2O gas, giving me Fe2O3 plus H2 gas. So this is liquid. That's 4. And there is 2. So see what we have here. Wait, is this equation balanced? No, it's not balanced. I'm coming. Okay, sorry. This is Fe3O4. I'm coming. Fe3O4. Fe3O4. Then this 3 plus 4H2 gas. Aha. So we are writing equilibrium constant for this. We are writing equilibrium constant for this. We are writing the equilibrium constant for this. So listen attentively. Okay. So see what we have here. So how do we write the equilibrium constant? Now, solution. Pay attention. Don't forget, we are writing the product all over reactants, then raised to the power of the number of mole. The product over reactant raised to the power of the number of mole. And please take note that we only see, look at this note here, very important. Note, we don't include pure solids and pure liquids in the expression of KC. We don't include pure solids and pure liquids in the expression of KC. That is, wherever you see anything like pure solid and pure liquid, don't include it because their concentration is equal to 1. The concentration of pure solid and pure liquid is equal to 1. So we don't always include it. Now let us write the first one. How will you answer the question? JAM normally asks and WAEC normally asks this question. Now look at this. I have 2H2 plus O2 giving me 2H2. How do you write the expression for the equilibrium constant? We say Kc equal to, the product is H2O. You now ask yourself, what is the number of mole beside H2O? That is 2. Then you now say raised to power 2. Then over, look at all of them are all gaseous. So there's no solid here, there's no liquid here. So I'm including all of them. If you see solid or liquid, we don't include them. So looking at this, Kc equal to, the product is H2O, then raised to power 2 over, look at this one, H2 raised to power what?
2.
Now H2 raised to power what? 2. Then O2 raised to power 1.
Oxygen.
Oxygen raised to power 1. What you are going to be putting at their power is the number you see beside them, their moles, and that's all. Let's look at question B. We have 2SO2 gas plus O2 gas, reversible reaction, giving us 2SO3 gas. What do we do? It's very simple. The expression for the equilibrium constant. Now check. All of them are all gaseous species. We don't have pure solid. We don't have pure liquid. It means that we are including all of them in the expression for the equilibrium constant. Now let's go. We start with the product, SO3. What number of mole will I put? Just check the number beside it. That is 2 raised to power 2. All over, look at the reactants. SO2 raised to power 2. And then O2 raised to power 1. As easy as that. It is very simple. That's how we write it. Products over reactants to the power of what? The number of mole. To the power of the number of mole. Okay.
Mr. Salah, I have a question.
Yes, sir. Okay, sir.
Now, according to math, we know that a base to the power of 1, apart from 0, is equals to that thing. So,
yes,
in first example and second one, that was that O2 raised to power 1.
yes.
Do we need to put the word?
Yes,
the
so
word raised to power
it.
1 here?
No, it's not. It's not. In fact, options we even see one day. I'm seeing a jam question like no, but just take note that what 1 was there, but it's not compulsory you put the 1. Okay.
Okay.
Yeah. Jam question don't even put the 1. Like you will see options that don't. But just know anything raised to power 1 is that thing. So it's possible in chemistry here too. Yeah. So now let's look at the third question. C. The third question, C, is a little bit technical. About this question, this particular question, you see it in WAEC and JAM. Now, see what we have here. How do we write the expression for the equilibrium constant? Guys, please pay attention to something. Before you write, anywhere you see pure solid or pure liquid, cancel them away. Now, look at solid here. Then, cancel this away. Look at liquid here. Cancel this away. So you are left with this and this. Now, write the expression for the equilibrium constant for all you have. Take away solid, take away liquid. Now let's go. I have Kc equal my product H2, then to the power of 4. My reactant H2O to the power of 4. This bracket should be, you see this square bracket I'm making use of. This bracket is very important. Now we use for concentration. So that is how we write equilibrium constant. Okay, let me give us a classwork now. I want everybody to write the equilibrium constant for the one I'm about to write. Okay, write the equilibrium constant for this. Write the equilibrium constant for this. I have CO2 gas plus H2 gas write the equilibrium constant for this. I'll give you 10 seconds to solve this. Write the equilibrium constant. Write the equilibrium constant for this in 10 seconds. Are we done? It's 10 seconds already. If you are done, unmute your mic and tell us your answer.
Okay, sir. The
Wait,
case
that
is
girl, no, don't talk. Another person. I'm familiar with that voice, baby. Another person. I want
okay,
a guy.
sir. We
Wait, I
have
want a guy. No, I want a boy.
So the answer is
two
C.
people.
No,
The answer
hey,
is
a boy, please. A boy, wait, don't worry. I want a boy to tell me the answer. I want a boy to tell me the answer. Any boys in the house? Let me check names. If I see the names, I will know. Very sure. Okay. So, okay, Aisha Olume, no, she's a female.
Adedara Okwaraji.
Ayo Ajomale, yeah, call this boy.
Ayo Ajomale, yes.
Tell us the answer. Ayola Eniola.
Thank you. Ogunton.
There are many here. There are many here. Kelechi Nathaniel.
Kelechi Nathaniel is a
Leah.
girl, and I want to answer. You said I should not
Okay,
answer.
oh, sorry. Like I'm used to
Leah.
Kelechi.
Open brackets.
Calm down. No. I don't want a female. I want a guy to tell me. And there's a reason I'm
I
telling
just
you.
accept the fact that girls are more
Let's
than
do it. Let's answer the question.
Hey, don't worry.
Let's answer the question and move on.
Wait. Okay, no guy that tell me the answer. Well, are they in this class?
You say
Or they're not general love their phones.
Sir,
Okay, yeah. Tell me. Okay, yeah.
the product.
What's your name? Your name.
And,
Okay, good. Yeah, tell me your answer. KC equal to what?
equals to H2
H2O.
and Cu
And CO. Okay.
over CO2 plus H2.
Over
CO2 into bracket H2.
CO2 bracket H2. Nice one. Correct.
Wow.
Correct. That's very good. That's very good. Okay, I'll write another one again. So again, will tell me the answer. I'll write another one again. Again, will tell me the answer. Okay. Okay, again, will tell me the answer to this. Write the equilibrium constant to this. Okay, I want to write the one that is okay. Okay, do you have any girl there? Now look at this equilibrium constant for this.
What?
I don't want so we have girls here like okay. Aisha Olume. We have Ayola Eniola Abi. That's a girl. Daniela Abi. We have Deborah. Deborah, tell me the answer.
so we can't see your board clearly.
You can't
Please
stop
just
watching.
because you're
Yes.
putting it full screen, so it's not clear, like it's cropped.
Yeah, because I minimized to the next app. That was why. Okay. Which guy is going to tell me the answer? Any girl in the
The
line?
answer is just B R2 because the next one is the liquid, and liquid is not included.
Okay. The answer is B, right?
BR2.
Please, if you are not talking, mute your mic, please. This is the answer, okay? Everybody, is she correct?
No, she's wrong. Sir,
Okay,
can I
good.
say it?
How am I wrong?
Wait,
How am I wrong? Liquid is not included.
wait. Another person should tell me the answer. I need another person. Okay.
1 over.
Yes, sir, that's the
So
answer.
this
So I
answer,
guess we don't have equilibrium constant.
this answer is by Kelechi. Another person. Next year. Another person.
Okay.
Do we have a guy that
Shukuro, as in what Shukuro is raising her hand.
Okay,
Shukuro.
okay. Unmute yourself. Unmute yourself. Unmute yourself.
Shukuro sọ̀rọ̀. Time on law.
Like, can they recap
Please.
the question back?
So look at the question. So this is the question. You want to write the equilibrium constant for this II. For this one, equilibrium constant Kc equal to what? Oh no, bro. So any guy, please. The girls don't know the answer. Any guys?
Yes, sir. Yes, sir. I want to say it.
Okay, no problem. Continue, sir.
1 over
I want to
BR2.
say it. Oh.
1 over BR2. Yeah, this is the correct one. Why this one is wrong? This one, okay, I will tell you why. Forget I told you something. See, wherever you see liquid, cancel it out. But make sure that, see, if you are writing equilibrium constant, we say product over reactant. See, we don't have any product again. We have cancel it out. So just say you have 1, then over your reactants, BR2. Yeah, this is how to write it, okay? This is how to write it. Good. So we've learned how to write equilibrium constant. We've learned how to write equilibrium constant, Kc. So for this level, we are looking at Kc only. So we have done that. No, so after that, for WAEC and JAMB level, the next thing you should know is Le Chatelier's principle. Le Chatelier's principle. What JAMB usually tests? Equilibrium constant and this principle. Very well. So please pay attention more on this aspect. Le Chatelier's principle.
Sorry, sir.
Yes, I can hear you.
I have a question.
Okay,
But why is it 1
Yeah.
over BR?
Okay, pay attention. Hello, I will explain again. Please check here. That guy that has the question, just check here. You will understand now. It's very simple. It's very simple. Now, hello, I want to explain to you now. Are you listening?
Yes,
Now,
sir.
Kc equal to, don't worry, write for everything. Products over reactants. Are you there? But don't forget that this one is liquid, Abi. Now, what did I tell you
Mr.
about?
Saula. Mr.
Huh?
Saula.
Huh?
Sorry, please. Can you remove that that what Shukuro of a thing? Because like I don't know what probably she is with a guy and they are disturbing what themselves.
Oh, okay. Hey, that guy disturbing my class. We will remove you now. Okay. So now don't forget that guy, that boy that asked the question. I told us that whenever you see a pure solid or a pure liquid, their concentration is equal to 1. Their concentration is equal to 1. So therefore, look at this one now. This is a liquid. The product says a liquid. So what's the concentration of this one? This is equal to what? 1. So therefore, my answer is 1 over BR2. Do you see that?
Yes, sir. Yes, sir. Yes, sir.
Exactly, 1 over BR2. So let me do the chatlier on the next page. No, I'll send the note across to us. If you are not able to write fast, don't worry.
Excuse me, sir.
Okay.
Sorry. When you made a statement that said since is 1, that is anything over 1 is still that same distance. So you said that
No.
there's
What
no
we said
need
is
of
something raised to power 1. What we said is, let me say I have something raised to power 1. If we're referring to power, it is still BR2.
Okay.
Yeah, it is power we're referring to. Yeah. Okay, good.
Okay, sir.
Good.
Thank you.
Now let's now look at the next page. Now we've learned how to write equilibrium constants. If you have practiced what is here, it is sufficient for you. Let's go. Next page. If you are not able to write fast, don't worry. After the class, the note will be sent across. So let's look at the Chatlier's principle. Le Chatelier's principle states that, let me quickly write it. Le Chatelier's principle states that if an external constraint is imposed on a chemical system in equilibrium, the equilibrium position will shift to neutralize the effect. To neutralize the effect. This is the law. It says that what? If an external constraint is imposed on a chemical system in equilibrium, the equilibrium position will do what? Will shift to what? Neutralize the effect. The equilibrium position will shift to neutralize the effect. Yeah. You see, pay attention. My goal here is to teach you how to know where the equilibrium position will shift to. Pay attention. My work here is to tell you how to know where the equilibrium position will shift to, whether left or right, because JAMB will really test you on that. Now, pay attention to me. You see, there are three factors that affect chemical system in equilibrium. There are what? See, we have three factors that affect chemical system in equilibrium. Now, what are those three factors? There are three. 1, 2, 3. There are three. Which are what? Let me start from temperature, concentration, and pressure. Temperature, concentration, and pressure. Now, pay attention. There is a question they always ask that: does catalyst affect equilibrium position? Does catalyst affect equilibrium position? That is catalyst among those factors that can affect equilibrium position? Please, the answer is what? No. Please, catalyst is not among the factor. But catalyst can just help you speed up the rate at which equilibrium can be achieved, but it can never change equilibrium position. That is, catalyst cannot move equilibrium position to left or right. It's not possible. So catalyst is not among the factor. Don't forget, chemical equilibrium, catalyst is not among the factor. Please don't forget. The only three factors that affect are what? Temperature, concentration, and pressure. Now, what JAMB will now test is that how do temperature affect, how do concentration affect, and how do pressure affect? Now, pay maximum attention. Pay maximum attention, please. Pay maximum attention. I want to teach you how the three of them. I want to teach you in a way that you will understand without cramming anything. You don't need to cram anything. Now, let's go. Effect of temperature. Let's see how temperature will affect. Now, pay attention. How temperature will affect. Let's see how temperature will affect. Let's see how temperature will affect. Good. Now, let's see how temperature will affect. Now, look at something like this. We're giving you, see, we gave you something like this. Now check. Let me put it there. We give something like this. 3H2 gas plus N2 gas to give us NH3 gas to NH3. And you were given this information that the enthalpy change is negative. Thank God, yesterday, day before yesterday, that's our previous class, we did thermochemistry. When enthalpy change is negative, who can tell us what it means? What does it mean? Is it endothermic? Exothermic. Thank you very much. You can see why we did thermochemistry before chemical equilibrium. Good. Now, pay attention to something. You see, if Jamb want to ask you question,
A student want to ask question, Mr. Salah.
okay,
Mr.
okay, ask please.
Rayo, go on.
Sir, it was a mistake.
Okay, no question.
I will beat you.
Okay. Now pay attention to something. Now, don't forget that exothermic reaction always release heat. Don't forget, exothermic reaction always release heat. Now pay attention to something. Since this reaction is exothermic, it releases heat. You know that when something releases heat, if you touch it, it will be hot, right? Good. It means that since this thing is releasing heat, the forward reaction is hot and the backward reaction is what? Is cold. Let me tell you something. There's something about thermochemical equation is that if the forward one is hot, the backward one will do the opposite. It will be cold, and vice versa. Okay, how was I able to get hot and cold? Pay attention. Is that what I'm having here is exothermic. Exothermic is releasing heat. So therefore, I'll say this is hot and this is cold. Now pay attention. Jam will now ask you this question. That increase in temperature, where does it favor? Does it favor forward reaction or backward reaction? How do we do that? Now, pay attention. Increase in temperature favors where? Everybody pay attention. Assuming you have two food on your table, one is very hot and one is very cold. Now, if you are to warm any of this food, which one will you warm? The hot one or the cold one? Who will tell me? You have two food on your table, one is hot and one is cold. If you are to move anyone to your microwave to warm it, which one will you warm? Is it the hot food or the cold food? Who knows?
There is the cold one.
Is the cold one. Good. You cannot warm something that is hot or is a cold one. It means that increase in temperature will favor that side that is cold. It means that increase in temperature will favor now. Which side is cold? Is it the forward or the backward? The backward. Therefore, increase in temperature favors the backward reaction. Favors the backward reaction. You see, there are several ways you can use to say this word. You can say increase in temperature favors the backward reaction, or you say increase in temperature shifts the equilibrium position to the left. This is left or backward. This is right or forward. Exactly. So increase temperature favor what? The backward reaction. Yeah, correct. Now, let us now look at the second one. Decrease in temperature. Decrease in temperature favors where? Now, you have two food on your table. One is cold, one is hot. And you know that there are some people like me. I don't like eating something that is very hot. If you serve me hot food, I can't eat. I don't like hot food. So I'll make it cool. So it means that if I have two food on my table, one is cold, one is hot, I can eat this cold one. If I'm to cool the temperature of any of them, I'll go and cool the temperature of the hot one. Therefore, what will I say? Decrease in temperature favors that side that is hot. That's favor the what? The forward reaction. Favors the forward reaction. Everybody, that is it. It is very simple. It is very simple. As simple as that. As simple as that. As simple as that.
Mr. Salah.
Yes, sir.
Please, I just want to confirm something. So,
okay, sir.
Are you saying that irrespective of the reaction,
yes,
will favor the backward reaction, and decrease temperature will always favor the
no, it's
forward
not all the time. Let us look at another reaction. Wait, I'm coming. Wait, I'm coming. Let us look at another reaction. It's
like
not
I mean,
only
mean when delta H is all negative.
yes, all the time. All the time, yes.
So
All
when
the time.
delta H
Yes.
is negative,
That's what textbook will
all the
summarize.
time, increase in temperature will
Yes.
favor the backward reaction.
All the time, yes.
Why decrease in temperature will
Yes, exactly.
Okay. So that is
Yes,
what I
in
just
fact,
want
this is
to
what textbook will say. Textbook will tell us that, yeah, textbook will tell us that for an exothermic reaction, yeah, textbook will just summarize that, but this is how they actually got it. So all the time, if it is exothermic, all these are always true. All these are always true. Nice. So let us look at another one where it is not exothermic. Now look at this reaction. So 2N2O5 to 2N2O4 plus O2. Gas. And you have your delta H to be positive. Here, delta H is positive. Now, look at this one now. Delta H is positive. That means endothermic. That means endothermic. Now, pay attention, please. Endothermic. Endothermic means it is cold. So I have a cold part here, and this backward one will do the opposite. Hey. And this back one will do the opposite, which is what? Which is hot. I'm coming. I'm coming. Okay. Okay. Okay, let's go. So who can tell me if I increase the temperature, where will it favor? You want to make something hotter, where will it favor? Forward reaction or backward reaction? Who knows the answer? So you have something that is hot or cold, and you have to increase temperature. Which one will love increase in temperature? Where will it favor?
The backward reaction.
Increase, look at it. Increase in temperature. Increase in temperature. If you want to make something hotter, increase in temperature favors where?
Forward
Yes.
reaction.
Yes, favors forward reaction. Yeah, favors forward reaction. Good. Why decrease in temperature will favor where? Decrease in temperature will favor where?
Backward
The
reaction.
backward reaction.
Yeah, favors the backward reaction. Exactly. Favors the backward reaction. Good. That's that. Please let us quickly move. Let's quickly move to the next one. Effects of concentration. Effect of concentration. Okay. Okay. Now, for effect of concentration, let me just give you a cheat. Let me just give you a cheat. This is the cheat here. This is the cheat I want to give you. Okay. The reaction, please jot this thing down. The reaction always favor. The reaction always favor, write it this way. Always favor the side with the lower concentration. If you cannot just this small thing, you are good to go. The reaction always favor the side with the lower concentration. Simple. If you can see the two sides, reactant and product, if you can spot anyone with lower concentration, then that is where the reaction will always favor. Let me tell you something. You see, in a layman language, how can we explain concentration? That is, if you have high amount of something, you have high amount of that you have higher concentration of that thing. Let me say I have 20 students in a class, and I pack more students inside that class. It means that what I'm increasing the concentration of students in the class. That's it. So let me say, look at this upper reaction now. Let me say I'm increasing O2. I'm increasing O2. It means that I'm increasing concentration of O2. Now, everybody, let us look at this reaction. this same reaction up. Please, oh, don't forget, it will always favor the side with the smallest concentration. With the smallest concentration. Don't forget, with the smallest concentration. Good. Oh yeah, now I want to ask a question. See, the question is this. Adding more O2. Please pay attention. What did I say? Adding more O2, what happens? See, if I add more oxygen, now, which part will be in the highest concentration? Is it the reactant? Is it the product or the reactant? Check what is happening here. We went to be adding more oxygen into the system. Now, as we are adding more oxygen, tell me, is it product that is increasing or reactant that is increasing? Can you guys tell me? If you are adding more O2, more oxygen.
Reactants.
Wait,
Reactants.
If I'm adding more oxygen, remember that I'm increasing product concentration. Do you see that? Like I'm increasing product, that's what I'm doing actually. If I'm adding more oxygen, I'm increasing the concentration of the product. Now, pay attention. Look at this statement. The reaction always favor the side with the lower concentration. Now, as I'm increasing O2, the side with lower concentration is the reactant. Therefore, adding more O2 favors the backward reaction. Aha. I will explain that again so you get it very well. See, it's very okay. I think let me do something. I have water here. Check this thing. I have water here and I have Coke here. Pay attention to these two things. Pay attention to these two things. See, look at this reaction between water and Coke. Now, check something out. Please, if I'm adding more Coke to this thing, if I'm not adding anything to water, I'm adding more Coke to this. Everybody knows that what this part will be increasing. That is, the concentration of this product will be increasing. Correct? As it is increasing, according to my statement, it will favor the side that is not increasing. It will favor the side with the smallest concentration. As I'm putting more Coke, Coke is getting higher. Therefore, it will favor this other part, water. That's what I'm doing here. So if you add more oxygen, it favors the backward reaction that you are not doing anything to. That you are not doing anything to. Now, look at this one again. Let me say I adding more N2O5. What will happen? Everybody check this thing out. So you get it once and for all. Check it out. I am adding more reactants. It means that concentration of the reactant will be increasing. So this one will be of higher concentration. And don't forget, when we are doing effect of concentration, it will always favor where we have lower concentration. I'm adding more of this. This is already higher. The part with the lower concentration is the what? Reactant. So it favors the forward reaction. It will favor the forward reaction. That's it. That's it. That's it. Okay. Let me now change the pattern of the question. Now, let me now say that, everybody check, look at it very well. Let me now say, I now remove. Removal of O2. Everybody check. I'm removing O2 now. Everybody look at this reaction. I'm now removing O2. As O2 is being formed, I'm removing it. Now, check. I'm removing the products, but I did not do anything to the reactants. Who can tell me which parts have the highest concentration? I'm removing the product. I'm removing the products, and I did not do anything to the reactants. So which parts have the highest concentration? Who knows? Product or reactant?
The reactant.
Exactly. Check. I'm removing O2. It means that what the reactant, I'm removing O2. It means that what this one will be decreasing. So the whole of the product is decreasing. So this one will be of higher concentration. And don't forget, for effect of concentration, the reaction will always favor the part with the lowest concentration. So as I'm removing O2, the reaction will favor the side with the lowest concentration, and that's what the products where you are removing, and so on like that. So that's it.
Excuse me, sir,
and so on like
please.
that.
I have a question.
Yes. Okay, ask.
Okay, sir, you said it will favor removing O2, it will favor the product, right?
Yes.
Okay, but there are
Yes.
same moles, like 2 moles here and 2 moles here. Are they not equal?
Wait, I'm coming. Let me write the reaction again so you relate with it very well. You have
Oh,
2N2O4.
yeah.
See, pay attention. I was removing this away. So it
Yes.
means that this part will be decreasing. And this part will be decreasing. And this one, normally, nothing is happening to it. So this part will be decreasing. And this reactants, so in other words, I can say my product is decreasing. Since my product is decreasing, if I ask you that which part has the lowest concentration, is this part that is decreasing? Because I'm not removing reactants. I want to be removing products. And the trick of this thing is that just check where I have smallest concentration. As I'm removing oxygen, everything here is decreasing. So as it's decreasing, the reaction will favor it. That's it.
Okay, please, sir, let's assume the oxygen was not there. It was just the 2 moles of this and the 2 moles of what would be
There's no
the
problem. Okay, no problem. I'll write it like that. Okay, let me say you are being given something like this. Check. N2O4, 2NO2. Something like this. Yeah.
Yes, sir.
Oh, yeah, now look at this one now. Let me say I went to be removing NO2. As it's being formed, I'm removing it. Now, who cannot tell me which part have the highest concentration, reactant or product?
Okay, it's reactant.
Reactants. And where do we the reaction favor? Is it the highest concentration or lowest concentration?
The lowest
According
concentration.
Exactly. So according to this, exactly. So it will favor the product forward reaction. That's it.
Okay.
Yeah. So
Okay,
the one for
sir,
pressure
but
is this. Yeah. I can hear you. Continue.
that was not my question.
Okay. What's the question?
What I was saying is that, yeah, I was asking if, like, they give you 2 moles on the product side and 2 moles of a concentration on the reactant side, and they
Okay.
ask you an increase in, or I don't even know if there's anything like an increase in concentration, which side will it affect?
Okay,
Would they
please.
give you like
Okay.
the
Okay, let me say that. Okay, for example, you have something like this. Wait, you now have, let me say, for example, you have something like this. It's something like this. Hello. Are you there?
Yes, sir. Yes.
Okay, something like
That's
this.
it.
Yeah, I'm coming. Someone wants to join the class. Okay, yes. It's the same principle. Okay, let me say they said that they increase the what? Why did they say they increase? They increase the top, please.
Concentration.
Of the what?
Okay, will they give you like what I was asking? Would they give like the particular?
Yes, they will tell you. Don't worry.
Particular
When we are
physics.
solving jam question, you will know. Just take note
Okay.
of this one. Don't worry. When we are solving jam question, you will see how they ask. Yes.
Okay, sir.
Don't worry. When we are solving past questions, you will see. Just flow with this trick and this shortcut. Whenever I'm solving past question, I'll be using this same trick to solve it. So let's go. Don't worry. Let us just move. Now, the last one is for pressure. And pressure is the simplest one. Effect of pressure. Pressure is the simplest one. Now, everybody check. Increase in pressure favors the side. I'm coming. Favors the side with the lowest number of mole. With the lowest number of mole. While decrease in pressure favors the side with the highest number of mole. This thing coincides with Boyle's law a lot. Yes. So just take note that what. See, let me help you and draw a diagram. If you see that diagram, you remember. You see, increase in pressure, we always favor the side with the smallest number of mole. And decrease in pressure, we favor the side with the highest number of mole. Yeah. And note these facts. If the number of mole of gaseous reactants is equal to the number of mole of gaseous products, are you there? Note that pressure has no effect. Pressure has no effect. Okay, please take note of all this fact that is here. I'm coming. Take note of all this fact that is here. I'm coming. Please hold on. Yeah, I said if you increase pressure, it favors the side with the smallest mole. If you decrease pressure, it favors the side with the highest mole. Okay, let us follow that pattern. Let's follow that pattern to solve this question. Everybody check. This one is the simplest one. If I have, let me say I have 2H2 gas. Please, when you are dealing with pressure, look at that gas very well. That's what we have business with. And H2O gas. Everybody, look at this. If you want to know how pressure will affect, firstly, what is the number of mole of all the reactants? I have 2 here. I have 1 here. 2 plus 1 is 3 moles. So my gaseous reactant are 3 moles. My product, how many moles do I have? Just 2 moles. Now, I have 3 moles on the reactant, 2 moles on the product. Now, don't forget the trick. If I increase pressure, it will favor the side with the smallest mole. Which side is the smallest mole? This is what I have. This is the smallest mole. And here, this is the highest mole. So this is very simple now. So who can tell me, if I increase pressure, where will it favor? Forward reaction or backward reaction?
Forward reaction.
Forward reaction here, because see, increase in pressure will favor the smallest mole. If I decrease pressure, where will it favor? Backward reaction. Don't forget, decrease in pressure favor the highest number of mole. Favors the highest number of mole. That's just it. It is not hard. It's just as simple as that. Now, I want the boys to do this. I just need an answer. Will pressure affect this? So this for the boys and this for the girls. Don't forget I told you a fact here that. I told you a fact here. What is that fact? If the number of mole of gaseous products is equal to the number of mole of gaseous reactants, pressure do not have effect. Now let the boy tell me, will pressure have effect on this? My battery is getting low. Will pressure have effect on this first one? Tell me quickly. My battery is about to shut down. Will pressure have effect? Will pressure have effect?
No, sir.
No, it won't have effect because check. I have 2 here. 1, I have 2 here. So pressure do not have effects. Let me do the second one also. Or who will do the second one for us? Any girl will do the second one for us?
Let's do the second one. The pressure has no effect since pressure deals with gaseous substances. So if you check very well, Fe is a solid. So we have we have equal moles in the two gases, so pressure has no effect in the both reactions.
Correct, exactly. This is a solid, this is a liquid. So number of mole of gaseous reactant is 4. Number of mole of gaseous product is 4. Therefore, pressure has no effect. I'll send the note across to us because